When any protective scheme is newly installed, it must be thoroughly checked and tested before placing it into operational service. Commissioning covers a very wide range of activities, as we shall see. In many cases, the protective scheme forms part of a completely new power installation, or perhaps an extension to an existing substation or generating station. Commissioning of the protective equipment must be carried out in conjunction with commissioning the primary equipment, such as transformers, generators, bus arrangements, transmission lines, feeders, and so on. Several different groups of personnel will be involved in this overall task. Typically, installation contractors, equipment manufacturers, and power company representatives. The power company personnel will be from different departments, each with a specific field of responsibility. The engineering and construction department to inspect and test the primary equipment. The protection personnel to test and commission the protective schemes, and the operators to determine switching procedures and take over operation of the installation. A great deal of planning must be done before the commissioning tests begin. This ensures that the commissioning tests are performed in a safe, logical order, and that no item is overlooked. As several different groups are working around the equipment, it is essential that all safety rules and procedures be strictly observed. The work should be performed under any necessary permits required, typically a permit to work or a permit to test. All documentation and report forms must be ready, as it is essential to keep accurate records of all tests and operations. The recorded figures provide a benchmark for comparison of future routine test results. This information could also provide the basis of a claim against manufacturers or contractors in the event of unacceptable work. It could also be used in testimony before a utility commission or in court. The objectives of the commissioning tests are to prove that the equipment has not been damaged in transit, prove that the equipment has been correctly installed, prove that the protection system performs according to specification, and that the design and specifications of the protection system are appropriate to the system it is intended to protect, and prove that it is safe to connect the new installation to the power system. A typical list of commissioning tasks for all equipment is included in your workbook. Take time to study this list in detail. Before any equipment can be energized, it is essential that the related protective schemes be tested and placed in service, even though further adjustment may be required later. This videotape focuses on the commissioning tests related to protective schemes, even though reference may be made from time to time to primary equipment. Most power companies have their own set of commissioning procedures. Make sure you have access to these documents. Briefly, protection personnel activities should include the following: review of primary block diagrams, visual inspection of the primary equipment installation, review of protective scheme schematics, AC and DC, checking that the secondary wiring is correct, review of the results of circuit breaker tests, testing of CTs and VTs, secondary injection tests, primary injection tests, functional testing of tripping circuits, functional testing of alarm and annunciator circuits, phasing of primary circuits, testing of power supplies, on-load testing once the primary equipment has been energized, review of equipment instructional material, calibration of relays, review availability of appropriate test equipment, review safety requirements. We'll look at these tasks in greater detail as we proceed through this videotape. Prior to commissioning, the primary high-voltage equipment is not energized and is probably grounded at several points. As in all cases, work in this area must be protected by a permit to work. Clearly, one of your most important jobs is to become familiar with the installation. Regular trips should be made to site during the construction period. This will allow you to become acquainted with the physical layout of primary equipment, control panels, relay panels, and so on. Particularly note the location of CTs and VTs and the respective wiring. Often several sets of CTs are located in switchgear bushings or transformer bushings. Make sure that each CT is connected to the right device, be it metering, indication, alarm, or protection relays. It is essential that you thoroughly review the schematic diagrams for each of the protective schemes. Trace through these diagrams to get an understanding of the protection system. If you have any questions, as you probably will, make sure that you discuss these with your supervisor. You may well spot something that could cause problems later on. You should have a separate diagram for each protection and control loop. This is quite different from the wiring diagrams that will be used by the contractor for installation. These installation wiring diagrams are really geographical in nature, and any one diagram, say to a relay panel, may include several hundred connections and involve a multiple number of independent loops. You should check the wiring diagrams against your schematics to prove that the wiring really does achieve what it sets out to do. This is an extremely arduous task, but it will certainly help you become familiar with the installation. In certain installations, the schematic diagrams may not be available, and in this case, you'll have to make them up by inspection, that is, by extraction from the wiring diagrams. When the secondary wiring installation has been completed, it should be thoroughly checked to make sure that it complies with the schematics and wiring diagrams. Remember, part of the area may be operational and therefore energized, so you will need to take out a permit to work from the operator. Make sure that all terminal connections are tight. Also that fuses and links are properly wired and rated. Check nameplates on all control panels, relay panels, and equipment. In outdoor substations, make sure that the secondary equipment is weatherproof, and also that any specified heating and ventilating equipment is in service. Point-to-point continuity of the secondary wiring should have been already checked out by the contractor, but in some companies, complete checking is still carried out by protection personnel. You should at least check that the serial numbers on each wire correspond to the terminal number at every panel. Insulation resistance, that is, IR tests, must be carried out usually in conjunction with the contractor. Before commencing IR tests, make sure that the wiring is isolated, that is, no equipment is connected. Also ensure that all wiring grounds are removed. Check the insulation to ground and between each separate circuit. The insulation resistance varies, but should be between 1 and 10 megohms using a 500-volt megger. Finally, when testing of secondary wiring is completed, the permanent ground should be reconnected. Remember, this wiring is usually grounded at one single point only. Make sure that this is so. The secondary wiring can now be energized when required. These secondary wiring checks have covered the feeds from VTs and CTs to each particular relay on the panel. You should also make sure to check the control wiring from the relays to the circuit breakers and annunciator. This will usually be a DC circuit. Once the control circuits have all been checked out, The DC system can be energized from the battery and rectifier when this is available. This will enable operation of the circuit breakers to be checked. Of particular interest to the Protection and Relay Department are the recorded times for tripping and closing, including any inbuilt delay for reclosing. During these preliminary tests, it is usually convenient to check the voltage transformers. We need to test that the polarity is correct, and also check the insulation resistance and the turns ratio. Before conducting the tests, both the primary and secondary windings must be isolated from external circuits. The insulation resistance is checked between windings and between each phase and ground. One simple method of checking the polarity is by performing a flick or kick test. Each phase must be checked separately. A low-voltage DC battery is connected across the primary winding with the circuit interrupted by a push button. The positive side of the battery is connected to the polarity-marked terminal. A DC milliammeter with center zero is connected across the secondary winding, again with the positive connection to the polarity terminal. When the push button is closed, the ammeter will flick to the positive side if polarity markings are correct. When the circuit is opened by releasing the push button, the ammeter will flick to the negative side. The ratio test is carried out by applying a relatively low voltage, say 208 or 400 volts, to the single-phase primary high voltage side of the transformer, and accurately measuring the secondary voltage. From the two readings, the ratio can easily be calculated. For this test, the primary voltage supply should be fused in both lines, just in case there is a fault in the new transformer. Some companies use a ratio test set to perform these tests on transformers. Where a CCVT is used to measure voltage, check with your utility to see what check procedures are used. In all transformer testing, beware of applying low voltage to the secondary due to the hazardous high voltage induced in the primary. Okay, so now that we have tested the wiring to and from the relay, we have to test and calibrate the relays themselves. We must also ensure that operation of the relay results in the desired tripping function. We'll be looking at this in the next segment. For now, please switch off the tape and thoroughly review this material in your workbook. Before carrying out any electrical tests on the relays, it is first necessary to check their physical condition. The relay panel and general areas should be clean. In particular, the relay case itself must be thoroughly dusted before the cover is removed. Make sure that the relay is isolated, then examine the internal condition of the relay for signs of damage in transit. Make sure that all moving parts operate freely and that contacts make correctly. All terminal connections and other screws should be tightened. Examine the wires to make sure that none are broken. The target mechanism should be checked for operation and resetting. Report any discrepancy so that claims can be made on the supplier or contractor. Before leaving the manufacturer's works, it is to be expected that each relay will have been thoroughly tested to see that it meets specification. However, it is still necessary to perform functional tests on site with the relay in its installed location, and also to calibrate the relay for this particular installation. The necessary calculations and written instructions are issued by the power company's protection department. Relays are often tested in place by secondary injection. In this test, source input to the relay from CTs and VTs is isolated, and instead, AC current and voltage, where required, is injected into the relay to simulate fault conditions. In some cases, relays are removed from the panel and secondary injection tests performed on the workbench. Whenever a relay is withdrawn from the panel or the CT leads disconnected in any way, it is essential that a short circuit be connected across the CT secondary terminals. Otherwise, a dangerously high voltage could appear at the open circuited terminals. Even with zero load current in the primary, voltage could be induced into the secondary from electrostatic sources. Many different types of test set are available to supply suitably adjustable current and voltage to the relay. The test set must allow fine control and monitoring of test current, typically within the range 100 milliamps up to 50 amps. The test set may be fed from the local station power supply. Control is obtained by multiple transformer taps and an adjustable reactance or resistance. An accurate timepiece must also be included so as to record tripping times of the relay. Many types of relays require a test voltage that can be varied both in magnitude and phase angle relative to current. The test equipment includes a phase shifting transformer to allow the variation in phase angle. Make sure you are familiar with the test sets used in your company. Usually for test purposes, a test plug can be inserted at the base of the relay and sometimes also at the top of the relay. These boards effectively isolate the incoming circuits from the CTs and VTs. Apply a short circuit to the CTs and apply injection test current to the relay. On some other types of relay, the same result is achieved by switches at the base of the relay. On most relays, the following tests are performed. Insulation resistance test. The zero check to verify that the relay does not operate until the set values are reached. The value of pickup current, that is, the actual operating current at different tap settings. The inverse time characteristic where applicable. Operation of the target and seal-in circuit, plus other tests particular to the type of relay. There are a great number of variations in types of relays, their test requirements, and test equipment. The precise test and calibration procedure for each specific relay is spelled out in the manufacturer's instruction manual. Make sure that you refer to this when performing test work. You may also refer to the L&K video training series on test and calibration of specific relays. You must also follow your own company procedures in performing any test and calibration activities. Maintaining accurate records is vital. All test results must be carefully noted and final calibration settings registered. Make sure you are familiar with your own company documentation requirements. After the relays have been checked out and calibrated, functional tests of the tripping circuits must be performed. The objective of function tests or operation tests is to verify that when a particular relay operates, its output produces the desired action. Typically, relay operation may trip one or more breakers, initiate appropriate alarms and annunciators, block operation of certain breakers, complete a permissive circuit so as to enable other circuits to function, or trigger operation of a power line carrier circuit or other communication channel. I'm sure that you can think of many other protection relay functions. In order to perform functional tests, the relay panels must be energized with secondary AC and DC voltage. This means that the power supply system, including batteries, rectifiers, inverters, and emergency switching arrangements, must all have been tested and placed in service. One simple method of performing functional tests is to mechanically operate the relay by physically closing the appropriate contacts In this example, an overcurrent relay. In the simplest circuits, this relay output will apply DC to the tripping circuit and so cause the appropriate breaker to open and initiate the corresponding alarm and annunciator. If we are carrying out a series of tests, we do not want the circuit breaker to repeatedly open and close. In this case, it is usual to isolate the particular trip circuit using isolation links or blocking switches, and provide other means of indication, perhaps a lamp or voltmeter. In many cases, the relay output energizes one or more auxiliary relays, each of which have multiple contacts. In this situation, there would be multiple output functions to check, either by observing the resultant action or alternatively by measuring the output signal to each function. Each auxiliary relay should also be tested for operating time and reset time to make sure that it complies with specification. In some types of relay, particularly solid-state relays, it may not be easy or even possible to mechanically operate the relay contacts. One way around this problem is to simulate the output signal by isolating the relay and injecting the appropriate DC voltage into the output circuit. A far better method is to apply secondary injection into the relay CT and VT inputs. This can be done at the relay itself, but it is preferable to test the whole circuit at the same time by injecting the signal at a more remote point, perhaps at the CT and VT secondary terminals themselves. Links and blocking switches are often provided for this purpose. Injection of the appropriate value of secondary current and voltage to simulate differing fault conditions will allow us to simultaneously test the secondary wiring, the protective scheme, the protective relays, auxiliary switches, and the resultant functions. Remember, in any particular protection scheme, several protection relays may be involved and several secondary inputs required to simulate fault conditions. Each functional test will need careful, detailed planning before execution. Functional testing will also need to be performed on other related items which are not truly part of the protection system. Depending upon the particular installation, these items may include remote and local controls, remote and local indicators, chart recorders such as oscillographs and sequence of events recorders, alarms and annunciators for all equipment, automatic controls for transformer pumps and fans, SCADA equipment, battery chargers, metering, carrier and tone equipment. Pre-commissioning tests will be done on intertripping devices. For example, on power line carrier, typical tests include check of power supplies to transmitter-receiver unit, adjust transmitter output and receiver sensitivity, check on-off operation and frequency shift, tune the line traps, tune the line coupling circuit, check signal attenuation, that is, loss of signal strength along the line under different conditions. That is, A with the line ungrounded, B with the line grounded beyond the line traps, and C with the line on load. To perform tests on carrier equipment, special electronic test gear is required. We'll be talking about this subject in detail in videotape PSP-13, which is entitled Power Line Carrier. With such a wide range of equipment and a large number of items to be tested, a checklist should be prepared during the planning stage. This will indicate the sequence of tests and the prescribed method. The precise methods for testing and commissioning equipment vary quite widely from company to company. Make sure you're familiar with your own company's procedures. When performing commissioning tests, make sure that every problem you find, and you will find them, is explained and resolved. Do not gloss over or fudge any test result, even though people are breathing down your neck, because the equipment must be placed in service. Pay attention to detail. It is a vital part of your job. Now, at this point, let's take a break, and then we'll come back and discuss more commissioning tests. Please switch off the tape and refer to your workbook. In the last segment, we noted that relays are calibrated independently of the CTs and VTs that provide source information. However, we may have a perfectly calibrated relay, but this will not function to protect the system if it's receiving information which does not accurately represent conditions on the primary system. For example, the CTs may be of the wrong type, or they may be damaged, or even wrongly connected. A vital part of the commissioning process is to carefully check all of the CTs. Most companies test CTs for insulation resistance, polarity, turns ratio, and the magnetizing curve. Let's look at these tests. We can now test the CT magnetizing curve using the secondary winding. This is often called the excitation test. With the CT primary open-circuited, a 60 or 50 hertz voltage is applied to the CT secondary, and the consequent secondary current flow is measured. As the magnitude of secondary voltage is raised, the corresponding values of secondary current are plotted. Study of the curve shows that beyond the knee, saturation occurs. For a small increase in excitation voltage, there is a very large increase in current. The knee point is often defined as that point where a 10% increase in excitation voltage, as you see here, results in a 50% increase in current. Above the knee of the curve, the CT secondary current will no longer accurately represent the primary current flow. The test curve must be compared to the appropriate specification for the type of CT installed. This test is important to verify that in each specific circuit, the CT is capable of accurately representing fault current flow, which may be up to 20 times normal rated load flow. We discussed this problem in earlier tapes, particularly in respect to bus protection. If the CT secondary has taps, then choose the highest tap that can be saturated by the available test voltage. Before starting the test, some utilities demagnetize the CT so that excitation readings are more accurate. Demagnetization is carried out by applying a voltage to the secondary winding high enough to cause saturation. The voltage is then decreased slowly to 0. Another important test is to check the CT ratio at the different tap settings. This is done by applying a nominal voltage, say 50 volts, across the highest tap, and then measuring the voltage appearing at the other tap positions. This should, of course, be proportional to the turns ratio at each tap. The polarity markings should be checked on all CTs. One method is to apply the flick test in a similar manner to that discussed earlier for the voltage transformer. Preferably, the test lead should be passed through the CT donut as the primary conductor. If this is not possible, the small DC current will have to be passed through the primary conductor itself, like this. Often, several CTs are fitted around the primary conductor in the same transformer or switchgear bushing. We need to check that there is no leakage of flux from one CT core to another, as this would distort all of the measurements. One way of checking this is to apply a voltage of about 100 volts across the secondary of each of the CTs in turn. The maximum tap should be selected. All of the other CT secondary terminals are shorted. Then, one at a time, each short is removed and the voltage checked. In every case, the reading should be close to 0. It is important to check that wiring from the CT itself to the outlet terminal box is correct. Before placing the protection system in service, be sure to open any CT shorting links connected across the CT secondary. Up to this point, we have been checking out each individual CT, one at a time. In practice, several CTs may be connected to an individual relay, such as a ground fault relay. In other cases, for example, bus differential protection, several sets of CTs are connected to each individual relay. So there is a reasonable chance that the connections may not be 100% correct. And this would, of course, result in incorrect operation or even non-operation of the protection scheme. One way of checking CT connections is by injecting three-phase test current into the three phases of the CT secondaries. Measurement at the relay panel will then establish that CTs are connected to the corresponding phase relay, and residual current measurement will prove that they are connected the right way around. Many companies check out CT connections by primary injection tests. In this method, low voltage test current is passed through the primary conductors themselves, and measurements are taken on the secondary side to prove that the CT connections are correct. In some installations, the CT is fitted with a test winding specifically for primary injection. In other cases, a temporary primary can be fed through the CT donut for test purposes. Before commencing any primary injection test, make sure that the primary circuits are isolated and available for test purposes. Take out a permit to test from the operators. You will probably have to remove grounds from the primary circuit. When applying the test connections, make sure that they make good contact, or you may get unreliable results. This diagrammatic arrangement shows three CTs, each connected to its own overcurrent relay, with the residual passing through a ground fault relay. At the relay panel, a low-impedance milliammeter is placed in series with the ground fault relay. The first test is to measure the CT ratio. Test current is passed through the primary of one CT only, say the A phase, and the corresponding secondary current is indicated by the milliammeter. The value of test current will depend upon the capacity of the test set and the CT ratio. With a CT ratio of, say, 500 to 5, a primary test current of 10 amps would provide a secondary value of 100 milliamps. With a CT ratio of 3,000 to 5, the same primary current would provide 16.6 milliamps. The CT ratio can be checked from these readings. This test should be carried out on all three CTs. The next test is to ensure that the CTs are connected the right way around, that is, they are in balance. For this test, a temporary short circuit is placed across the primary conductors. In this particular example, test current is passed through the A phase CT primary conductor, and then back through the B phase CT in the opposite direction. The resultant CT secondary currents should cancel each other out. If the CT connections are correct, the residual current, which is being measured by the milliammeter, should be 0. In this test, we're checking the intermediate wiring right through the relay and including the relay connections. If one of the CTs had been connected the wrong way around, then the secondary currents would be additive instead of opposing. Consequently, the residual current indicated by the ammeter would be about twice the CT current. Clearly, at these low values of secondary current, great care must be taken in order to obtain accurate readings. Some companies use a larger test set in order to provide a higher value of primary test current, and so check operation of the relay itself in addition to verifying CT connections. Test sets may be rated up to, say, 10 kVA, with the capability of providing up to 1,000 amps at 10 volts. This arrangement shows generator differential protection. The test set is connected like this. Primary current is passed through one CT only, and the value increased until the corresponding relay operates. This value of test current indicates the value of fault current required in the primary to operate the relay. The test is repeated for each separate phase. To check the balance of these relays, it is necessary to circulate test current between two phases at a time. Remember, the windings are permanently connected together here. This is similar to the test that we performed earlier on the overcurrent relay. A similar set of tests would now be performed on the CTs at the other side of the generator. On the balance test, we would have to place a temporary short between the windings. But how can we check the differential relay for stability? That is to ensure that a through fault will not trip the generator. To do this, we need to check the interconnection of the CTs on either side of the generator. A convenient method would be to inject primary current from the test set and pass this through both sets of CTs, including the generator itself. However, it is probable that the test set will not have sufficient MVA capacity to overcome the impedance of the generator winding. The most common way of performing this test, particularly where a new generator is being commissioned, is to place a short circuit across the generator output and run the machine at very low excitation. This allows us to pass load current through the generator windings at low voltage and for a very small amount of power input from the prime mover. This is the established method for drying out the generator winding. It also provides us with an excellent opportunity to check secondary current input to all of the generator protection devices. Checking the CT connections for transformer differential protection is more complicated. Remember, where the transformer is connected in delta Y, the CT secondaries will be connected in Y delta. This factor must be allowed for when measuring secondary currents during the primary injection test. Where large, high-voltage transformers are concerned, it is likely that the test set will not have sufficient capacity to pass adequate test current through the transformer impedance. For this type of transformer, the test is usually performed by placing a short circuit across the low-voltage side of the transformer and energizing the high-voltage windings from a three-phase low-voltage supply, say 600 volts. This will probably be sufficient to pass a low current through the primary winding, 3.5 amps in this example. By carefully measuring current flow at the appropriate CT links, we can check CT ratio, CT polarities, CT circuit wiring, wiring of auxiliary CTs, wiring of differential relays. Clearly, primary injection tests can provide an excellent method for checking CT connections. We have looked at some typical examples, but make sure you check your own company procedures in this area. However, not all companies perform primary injection tests. Some prefer to rely upon comprehensive functional tests using secondary injection, followed by in-service tests when the primary installation is energized and carrying load. And we'll be talking about this in the next segment. For now, please switch off the tape and thoroughly review this material in your workbook. The purpose of in-service tests is to check the protection schemes under operating conditions, and that is with the primary equipment energized and on load. Energizing the primary equipment is usually the responsibility of one designated commissioning engineer, assisted by the operating personnel, the protection personnel, and other departments. Before energizing, they will make sure that all work has been completed, that all temporary grounds are removed, and that all permits to work are cleared. All protection relays should be in service, even though further adjustments may have to be made. Indeed, for the first energization, the protective relays may sometimes be temporarily set to give increased sensitivity. Before any primary equipment is connected into the existing power system, the phasing must be proved. In most installations, the primary circuitry is exposed so that a visual inspection can be made to ensure that the primary phasing is correct. That is, to make sure, for example, that the A phase of the bus is connected through the A phase circuit breaker and disconnects to the A phase of the transmission line. Similarly with the B and C phases. However, this visual inspection is not always possible. For example, a three-phase transformer has internal connections. Also remember, there will be a phase shift between primary and secondary for a Y-delta connection. In most cases, phasing of the transformer would have been tested during installation by applying a low voltage, say 600 volts, to the high voltage side and measuring voltages on the secondary. Plotting the resultant phasor diagram will prove the voltage ratio, phasing, the phase shift, and phase rotation. For voltages up to, say, 25 kV, phasing checks can be carried out by using insulated phasing sticks. These can be inserted into energized switchgear spouts or across open disconnects to check the voltage across the break for each phase. If phasing is correct, the voltage across the open contacts should be 0 or close to 0. However, if phase rotation is incorrect, a high voltage will appear across two of the phases. A typical list of general instructions for initial energization is included in your workbook. Let's consider an example of synchronizing a new generator to an existing bus which is energized. The generator is run up to speed and excited so as to provide the required test voltage, probably lower than nominal. This will apply voltage to the windings of both the unit step-up transformer and unit auxiliary transformer. Remember, both unit and auxiliary breakers remain open. The first task is to test the VTs which are connected to the generator terminals. Compare the secondary voltage to a known source to ensure it has correct phasing and phase rotation. Many VTs are fitted with a tertiary winding, which is connected in broken delta. Check this voltage. It should measure 0 or very low voltage. At this point, the generator terminal voltage can be raised to nominal value and voltage tests carried out on all protective relays. Clearly, before paralleling the new generator to the existing bus, we must ensure that phasing and phase rotation are identical on both sides. This may be done on the high voltage side of the unit transformer. Another method is to shut down the generator, open the terminal links, and backfeed the VTs by energizing the unit transformer from the high voltage side. Compare VT phasing and sequence to a known voltage, and with readings taken with the generator energizing the VTs. It's most important to make sure that the synchroscope is receiving correct information. It must be connected correctly to the VTs on either side. Remember, there will probably be a phase shift across the unit transformer, and this will have to be taken into account by the synchroscope connections. Once the generator is paralleled to the bus, load on the turbine generator can be raised sufficient to give adequate current readings on the CT secondaries, and so allow in-service readings to be taken at the CT links. As an example, let's look at in-service readings of the generator differential protection taken at the relay panel. Our objective is to test the magnitude and phase angle of current in each of the restraining coils and operating coils. A suitable ammeter and phase angle meter are connected to the circuit under test through the test board. The phase angle meter must be provided with a fixed voltage which can be used as reference in order to determine the phase angle and consequent direction of current. With a balanced load on the generator, the current passing through each relay operating coil should be at 0 or a very low value. On the other hand, current measured through the restraint coils should be equal to the CT secondary value. In any particular phase, the current through the restraint coils on either side should be 180 degrees apart. The current enters at one relay terminal and exits from the other. This is correct if there is no internal fault. If the test shows different phase angle relationships, then the CTs have been incorrectly connected. However, this problem should have been discovered earlier by secondary or primary injection tests. Transformer differential protection can be measured in a similar manner. But in this case, we should expect to see some current passing through the operating coil. As we pointed out in an earlier videotape, this error current or spill current is due primarily to the selection of transformer taps, plus the effect of dissimilar CTs on either side of the transformer. Obviously, the ratio of spill current to restraint current as measured during the test should be lower than the differential setting of the relay. As soon as possible, with load on the generator, the corresponding bus protection CTs must be checked for balance and secondary current magnitude and direction. When this test is completed, we should check at the protection relay panel that the summation of all the bus CTs is 0 or very close to 0. When a transmission line or feeder is energized from one end only, charging current will flow to feed the natural capacitance of the line. This may be sufficient to allow us to perform a preliminary check of the current balance in the CT secondaries. Preferably, a radial load should be connected at the far end of the line. In this manner, we can be absolutely sure of the direction of current flow when taking in-service readings. In order to check pilot protection, we need to take in-service readings at each end of the line by measuring the value of secondary current flowing in the operating coils and restraint coils. With a phase comparison scheme like this, we would expect to find 0 or very low current flowing in the relays and pilot wires. This would indicate that the CTs are correctly balanced. We can simulate a through fault, say a ground fault on phase A, by disconnecting the CT connections to phase B and C, not forgetting to place a short across the CTs. This is usually done at the test plug board like this. With this arrangement, we should have considerable current flowing through both restraint coils and the pilot wires. Current through the operating coil should be 0 or close to 0. However, if the relays at both ends operate incorrectly, then the pilot wire connections should be reversed at one end only and the test repeated. In many power companies, the standard test procedures indicate that for this type of test, the output tripping signal must be blocked. Of course, relay output to alarms, auxiliary relays, and other devices must remain. Moreover, this isolation is only permitted where sufficient residual protection and backup protection is available. Remember, duplicate protection is usually provided on important circuits. Great care must be taken in carrying out service checks on directional relays. Where voltage polarization is used, the voltage balance and phase sequence of the secondary voltages applied to the relay should be thoroughly checked as soon as the VTs are energized. Make sure that the connections agree with the wiring diagrams and the manufacturer's manual. For example, the A-phase directional relay may require voltage polarization from the B and C VTs. This is to provide the desired directional control. You'll remember we discussed this in earlier videotapes, specifically 2 and 9. To check the phase relay, the load current magnitude, direction, and power factor must be measured accurately. Also, the value of current and its phase angle provided to the phase A directional relay. The phase angle meter should use as a reference voltage the A phase to neutral VAN. If a phase angle meter is not available, a watt meter could be used with its voltage coil connected phase A to neutral. We must also accurately measure the voltage input to the relay and its phase angle relative to VAN. This will enable us to draw a phasor diagram indicating the relative phase displacements of current, IA, and the polarizing voltage. With current flowing in the designated tripping direction, usually into the line, the directional element contact should operate. This will act as a permissive to the overcurrent or other protective element, so tripping should not occur under normal operating conditions. To check the blocking element of the directional relay, we can simply reverse the flow of current to the relay by cross-connecting the CT connections at the test plug. In this situation, the directional element contacts should open. Before conducting any in-service tests, be sure to discuss the activity with the operators and alert them to possible inadvertent tripping. This will allow them to prepare contingency plans. Incidentally, when performing in-service checks, the sequence of events recorder should be in operation to help analyze any incidents. So we have looked here at just a few examples of in-service tests. Enough, I hope, to get us all thinking and to realize the excellent opportunity that these tests provide for checking out the complete protection schemes. Your utility company should have complete, detailed procedures for all in-service tests to be conducted on your specific protection schemes. Make sure you study this material and check any problem areas with your supervisor. I'm sure you'll find a few. When carrying out commissioning tests, remember that you are part of the overall commissioning team. All drawings should be marked up to show the actual as-built condition, including modifications made during the commissioning tests. These must be passed on to the appropriate engineering department. Also, inform the operators of any changes and any other pertinent information. Good communication and coordination is absolutely vital, and especially pay attention to safety procedures at all times. Please switch off the tape now and go through this material in your workbook.